to one of our potentially last lectures. I'm not sure if we'll complete it today. We'll find out. Um, we're going to be doing chapter 12, which is on solids. And because this chapter is so conceptual, there's not a whole lot of math or that sort of thing, and the drawings can be pretty complex. This is one I use PowerPoint for. So these slides are produced by the publisher of the book, and so they have the same images. So hopefully that reinforcement will help out here. So I'll be using that for this chapter, and I'll be posting these on Canvas so you have them as well. And yeah, we'll go from here. So with solids, we're going to see we have four major types that we can categorize solids into. And really, these categories arise from how the solids are held together. Because, we've spent so much time looking at individual molecules throughout the semester. And we know that these molecules can come as solids, liquids, or gases, right? And gases and liquids were really focused on individual things happening within those because solids and liquids are able to react, things are moving. With solids, we don't see that. So solids are pretty different. And so they're going to be held together through four different ways, and those will correspond with the four categories we have. So first we've got metallic solids. These are made of metals only, atomic metals, or we can throw some other things in there. We call those alloys, so we'll see that in a little bit. And we're going to see that those are held together because they have massive atomic or molecular orbitals that do that. And there's two models that we'll look at. One is called the electron C model, and one is using molecular orbitals, so we'll look at both of those. We have ionic solids, which are held together because of electrostatic attraction, so positives and negatives attracting each other, and we'll see that those alternate very nicely. So we have positive on one side, negative on the other. They're holding each other together. Next, we have covalent solids like diamonds. Diamonds, for example, are held together through covalent bonds only. And there we're talking millions and millions and millions and billions and trillions of covalent bonds holding these things together. So these are just networks. So very, very, very huge chains of these compounds. And then the last category we have are molecular solids, which are going to be made of molecules, covalent molecules, that are held together by intermolecular forces. And those can be hydrogen bonds, dipole interactions, or dispersion forces. So all of those will work there. So traditionally, these are typically like, with these, the London dispersion forces actually become pretty strong over the course of these. So we're going to see that many organic molecules like sugar, although sugar has hydrogen bonds, things like camphor or waxes, these are held together through dispersion forces, again, because these molecules get bigger and bigger, become more and more important. So let's look at metallic bonding in general here, and ionic bonding. And we're going to see that things can kind of fall into two categories. Within those two, we can have crystalline solids, which are going to form very regular, very specifically arranged configurations where we have predictable structures. This is perhaps most obvious in ionic solids, where we have solid or positive, negative, positive, negative, positive, negative, and it goes in three dimensions, right? If this is a positive, we have a negative here, 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 wherever, all the way around it, and that just repeats over and over and over again. And it's very regular, it's organized, it's orderly. Amorphous solids, on the other hand, like glass or obsidian, as is pictured here, don't have a nice arrangement. So really they look like liquids molecularly, but they just don't move. So remember, liquids are kind of just randomly moving about, and they're flowing all over each other, and there's not really any order there. And if you just kind of freeze that, like not literally freeze, well, maybe, depending on the solid, right? If you kind of stop time, that's what an amorphous solid will look like. So it's liquids if they stop moving. Whereas crystalline solids are very organized and orderly and predictable. And so as a result, you can see that some of these, like this pyrite example, you see that you have little cubes sticking out of each other. And that is represented in the fact that these atoms are arranged in cubic structures within those. And we'll look at those in the next coming slides here. We'll look at how these crystalline arrangements happen. And so we can see that there's kind of four major ways we can make crystal lattices. So lattices are just these repeating structures. And they're either going to just be rectangular or parallelograms. They're all parallelograms. And so just depending on the size of those sides of your parallelogram and the angles within them, you can come up with different shapes. So you can have oblique ones, which are kind of these rectangular parallelograms, so they're kind of just tilted to the side a little bit, and they are rectangular. You can have completely square ones, you can have rectangular ones, and you can have hexagonal ones as well. So these are more of a rhombus shape here. And those will have 120-degree angles on one side and then 60-degree angles on another. Nothing you have to memorize here. We're going to see that there are many different types of these, and this is just in 2 dimensions. And these are repeating units. So we just try to make the smallest repeating unit we can. And so whether that's usually just kind of a parallelogram shape here. We'll see that this is 2 dimensions. We'll look at these in 3 dimensions in a little bit. And we're going to see that these extend throughout the entire structure. So we look at just kind of one little small unit within the entire structure of the solid. And so this is, again, going to be similar to that, ionic solid, positive, negative, or something like that, where we have those 4 in a square, and we can talk about that particular square in 2 dimensions if we're so inclined, or we can talk about it in multiple dimensions. And so that particular, positive, negative, or I guess negative, positive, can be something like a square lattice, where we have them on these 4 corners, or it can be something that's got a bit more of angles to it, or maybe there's some distance between them. And so different ionic or metallic compounds will have different lattices that they will have. And so if we look further at these single units within them are called unit cells. And these unit cells we're going to look at in a little bit can come with a variety of different ways of filling them up. So unit cells, again, if we want to think about this in the most basic terms, would be something like your positive, negative, positive, negative, positive, negative, positive, negative, where that's 3 dimensions. So maybe I've got 4 atoms on the bottom, 4 atoms on the top, and again, they're opposite positive and negatives. That might be a unit cell. It's the smallest kind of thing we can look at that's a repeating structure within our lattice. And again, typically, in this course, we're looking at mostly just cubic things. So like that, where we have 4 atoms on the bottom, 4 atoms on top of those, with the alternating charges. And so those would be a unit cell. And those unit cells in 3 dimensions just repeat in all directions. And so you end up with a complete structure at the end of it. So if we go back just a little bit, that would be something like where we have these alternating positive, negative, or I guess the bigger one's the negative probably. Remember that anions are bigger than cations. Negative, positive, negative, positive, negative, positive, negative, positive, and then in the middle we have another negative. And we see that this kind of just alternates above and below, right? Where we have negative, positive, negative, and then positive, negative, positive, negative, positive, negative, as we go down the rows. And so this might be a unit cell. We can choose. It's pretty arbitrary what we like to do with it. And we're going to see that there are a bunch of different ways we can do this, and we're going to see that all of them have these kind of parallelogram shapes. Because if we try and use something like a pentagon, there's no way we can put these all together where we don't have empty space. So if we have a bunch of squares, we can just line those up together, or a bunch of rhombuses or rectangles, we can just line them up nicely together. So we don't really see anything besides these. We don't see anything besides hexagons and quadrilaterals here. And within those, we have a few different flavors, but we don't need to focus on those too much because we're going to focus on cubic ones. So with cubic cells, we have three kind of main ways of putting atoms into them. We have the simple cubic cell, which has got atoms in the corners. So a cube has 8 corners, so you've got 8 atom bits in there. And if you can imagine them as spheres, we kind of draw them as dots here to make it simple. But really they're more akin to spheres than dots. And you want to imagine them where the sphere that this cubic lattice has in this corner, this sphere and this sphere are just barely touching each other. So it's not as if there's all this empty space there. There will be some empty space, of course, but consider you want to imagine it such that the atoms are taking up as much space as possible within our unit cell. And so we'll have a big old sphere here, a big old sphere here. All of these will be big old spheres, and they're going to be taking up a portion of this. And for a simple cell, it's if I remember, I think it's somewhere around 57% of the cell is occupied by atoms, and the other 43 would be empty space there. With body-centered cubic, we have the same thing. We've got atoms at all the corners, all 8 corners, and then we also have one in the middle. And so we're going to end up now having even more of that space occupied. And so, again, we're going to have the corner atoms touching each other, and they're also going to be touching this central atom in the middle. And then the last case would be face-centered cubic. We've got all 8 corners, and now all the 6 faces also have an atom within them. So if you think about how this works in 3 dimensions, these structures keep repeating. With something like a face-centered cubic, we can take a look at some space-filling models. So let me just pop those open here so we can take a look at space-filling models. We can take a look at what those might look like. So these are terrible. Here's a good one. So if we take a look at another window real quick, let me pop this open so we can see it. With a face-centered cell like this, we're going to see that, again, we have each of these atoms in the corners, 8 of them, and then we also have atoms in all 6 faces. And so we can see that this one gets more and more efficient. We pack more and more things in here. This is called a face-centered cubic structure, where we, again, have all of these atoms packing together. We can take a look at the body-centered cubic as well, in just a little bit more detail. And so we see the body-centered cubic just has got this giant one atom in the center of it. But again, we see there's some empty space here in the faces. And so we see that actually face-centered cubic has the most density. It's got the most atoms per unit cell of all of those. And so we're going to see here that these 3 are kind of the most common. Many metallic and ionic solids fall into one of these 3. There are quite a few that fall into others, but these are the big 3 for us. And so these are going to be just repeated over space. So if we happen to just have, this is going to be something that's more of a network solid. And we're going to see here that we take this cell and we can repeat it infinitely in a plane. in 3 directions. So we can go XY, we can also go XZ, we can go YZ, which would be, I guess, pointing this way. And so we can have all these different directions here. And so we take a single unit cell with whatever it's got in it and repeat it infinitely. And for something like a covalent structure, a network solid like this, we have bonds forming in between unit cells. So the unit cell doesn't necessarily have to be, things that are bonded to each other directly, and there's no connection between them. These things just keep on going. Again, with an ionic example, of course, positive, negative, positive, negative. Of course, that just repeats on the next unit cell. So if this was positive, this was negative, then in our next cell we have another positive and another negative, and we can keep on going. And so we don't really stop at just one unit cell. These are all connected together, whether those are connected by covalent bonds or IMFs or ionic attractions. These things just keep on going. Oops. So let's take a look at metallic structure in more detail. So here are our our cubic unit cells again. So we again have the one where we just have it at the corners. We have the one with the corners and the middle, that's body centered. And then we have the one at the corners and all of them in the faces as well. And again, this is the most common one. And as we repeat these over and over, we get the entire crystal structure. So we kind of have layers here. We have single atoms, we've got unit cells, and then we have the entire crystal structure. And so these are what these things look like close up. And so we're going to see here that if we were so inclined, we could calculate how many atoms are within a unit cell. And so if we take a look at the simple cubic cell, or I guess it's called primitive sometimes, we see that each of those corners has 1/8 of an atom. Because if you imagine this cell repeating in all these different directions, we're going to see that each of these corners has 1/8 of that atom. And so the unit cell that's on top of it has another 1/8 of this atom, and the one to the side has another 1/8, and so on. And so they all occupy, they're in various different cells. And so each of these is 1/8 of an atom. If we have 8 corners, that's 8 times 1/8, which gives us 1 atom per cell overall. If we take a look at the body-centered cubic, we have an entire atom in the center, and then we have those 8 corner atoms. The corner atoms are still 1/8 of them. And so we have the 8 1/8ths in the corners. That adds up to 1. And then we have 1 in the middle, which is therefore 2 overall. And with face-centered cubic, each of these face ones is a half of an atom, because the face of a unit cell is shared between 2 unit cells. And so half of the atom is there. We have 6 faces. So that's 3 atoms in the faces. And then we have our 1 atom from all those 8 corners again, bringing us up to 4. So we see that the face-centered cubic has the most atoms per cell. And so it's going to be the most densely packed of all of those. All right, and then one more thing to note is that we're going to see that all of these will always try to maximize their interactions with each other. And so as a result, everything will be as close as possible. So your ions want to be as close as possible, right? Because they're positively and negative charged. They're attracted to each other. And so we're going to see with metallic bonding how that's going to look as well. But everything wants to be as close to each other as possible in solids. And so we call this close packing. And so we understand that everything is as close to each other as possible. That's going to make our descriptions of these unit cells a bit more appropriate. So everything will try and get as close to each other as possible. And we're going to see that when things are of different sizes, we'll have some slightly different structures. But when things are of similar sizes, they'll be able to get as close to each other as possible. Alrighty, so any questions so far on this kind of basics of how solids look molecularly at the atomic and molecular level? Hey, y'all are the quietest class, but that's neither here nor there, I suppose. So let's take a look further about metallic bonding. So with metals, we have some 90 some odd metals on the periodic table, right? But we are not limited to only 90 metallic solids, because we're going to see that we can mix them together. We can mix metals with other things to form alloys. And these things are going to be mostly metals. They're going to be solutions where your solvent is a metal. Often your solutes are other metals. Sometimes they can be nonmetals, though. And we're going to see that these end up changing your properties pretty drastically. And so, if you think about historically how, humans evolved, you go through, you've got your, Stone Age, you've got your Bronze Age, you've got your Iron Age and Steel Age, right? You've got all these different kind of landmark epochs of history that are defined by the alloys that they made. Because, if you're only limited to 90 different metallic materials, that's not very many. But they found, that when these things were mixed together in various proportions, you ended up with alloys that had drastically different properties. For example, gold is a pretty squishy metal. Pure gold, 24 karat gold, is very squishy. It's not very rigid at all. But if you take something like 14 karat gold, it's actually pretty hard. It's very hard to smash it together. And so the properties of it, even though it's mostly gold, can change drastically. And perhaps the most extreme example of this is steel. Steel predominantly is iron and carbon, and you can throw in other metals as well if you want to make it stainless. And steel has its own set of different things. You have different steels that have different carbon amounts within them. So you've got high carbon steel, you've got soft steel, as they're called, or high carbon steel can be called hardenable steel because you get very rigid edges. And then the less carbon you have in there, the more kind of flexible they are. So, these percentages here are just examples of various different alloys that you might see, that you might encounter. And the properties of these alloys will change greatly depending on the types of composition you have. If we want to take a look at various steel types, let's take a look at contemporary steels here. These are, what are these numbers? Well, let's just go on Wikipedia and take a look at various grades of steel. So steel is a very, very important alloy, right? One that is pretty, super strong, right? So if you think about all of these steels in here, there's all these different, I don't know what these numbers mean, but the point is, if we just take a look at all of these different ones, these all have various different properties. And it's all, they're all defined by the composition of those alloys. Carbon content of steel chart. Here, let's take a look at various steels. And you can see, presumably, let's see, give us some good ones here. No. Yeah, here we go. Here's a couple of them. So these are just three examples: A36 steel, 1040 steel, 1095 steel. Notice they just have various different amounts of iron, carbon, and other elements in there. And so these, have different properties. So 1095 steel, a high carbon steel, is meant for, knives and blades and that sort of thing, or you're looking at springs. If you want low carbon steel, these are things that are more flexible, and you can have ultra high carbon as well. So you can have all these sorts of different steels, and so you're not limited to just one alloy. The point of this is illustrating that you can have so many different types of steel, so many different alloys, depending on the composition that you have. And so for whatever your purpose is, you can make alloys that will suit that purpose. And so these things can be pretty exact in their compositions, which is very important for their properties. So again, there's not really any limits to the alloys you can make. You can mix whatever in whatever proportion and see what you get. And so some of the properties you want are: you can change the melting point, you can make it resist corrosion, you can make it easier to work. So all of these can change the physical properties of these metals. All right, so alloys come in two types. You can have substitutional alloys. These are the situation where your metals are of similar sizes. And so those are called substitutional alloys because you are taking the spot of one atom in your unit cell and fully replacing it with another. So for example, 14 karat gold, you take some of the gold atoms out and you replace them with silver atoms, and they just fit right into the place that those gold atoms used to be. The other kind is called an interstitial alloy. Perhaps, biologically, interstitial space is the space between cells filled with interstitial fluid. It's the same thing with a molecular structure. So we saw that there are spaces in between atoms within unit cells, and if you have a very small alloy or atom that you're adding in, for example, the size of iron and carbon is drastically different, right? Carbon's in period 2, iron's in period 4, and iron is to the left more on the periodic table, so iron is much larger than carbon is. So carbon can actually fit in between iron atoms. So you still have your iron unit cell, and you just have little carbons inserting themselves in between various iron spaces. And these are going to be called interstitial alloys. All right, so the difference here, substitutional alloys, the metals are of similar size. With interstitial alloys, your solute is going to be much smaller than your solvent atoms are. All right. And so if we're going to compare or take a look at how these things are bonded together, we're going to see that these actually don't do covalent bonding that we might expect based on how many electrons we have with them. We don't really worry about octets here. We don't worry about Lewis structures. That's stuff that we see with nonmetals. Nonmetals are the ones that are going to be dealing with these covalent bonds. We're going to see that aluminum, though, if we take a look at a particular aluminum atom, we see it's going to have 12 neighbors. It's hard to see in 2 dimensions, but if we take a look at this aluminum atom right here, it's got 1, 2, 3, 4, 5, 6, 7, 8, and then I don't know if you can see, but there's 9, 10, 11, 12 on the other side of it. So one aluminum atom actually has 12 neighbors, whereas if we consider something like a carbon atom or a silicon atom, we have 4 different neighbors that are covalently bonded. Phosphorus, we have 3, sulfur 2, and chlorine 1. And so we don't see that these bond together because they just don't have enough electrons to do that. Aluminum has 3 valence electrons. That would say that presumably it could bond to 3 others, but that just doesn't happen that way. We're going to see instead that these share all of their electrons together. And so the first model we have to describe this is the electron C model, where we have just all of these metals and their valence electrons are just completely dissociated, just going around wherever. And they're just shared throughout the entire structure. So an aluminum atom way over here, or whatever metal, and an aluminum atom way over here are actually sharing their electrons through space. So those electrons are just moving all the way through the entire structure all the time. And so, because those are completely dissociated, they're just moving around the entire time. And so they're held together because those electrons are moving around and we're having some electrostatic interactions there. And this explains also the ionic, or the ability of metals to conduct electricity. We know that electrical conduction is movement of electrons. And so if these electrons are completely delocalized, they're already separated from their atoms, we can apply electricity to them and all those will move around a lot faster. We can have them go in a line. And the malleability, which is the ability to deform without breaking, to squish them together. If you take a lump of metal and smack it with a hammer, it just spreads out a little bit. It deforms. It doesn't break. Because of this, you can see that with this model as well, because all you're doing is just moving that sea of electrons around. You're not actually breaking any bonds there. So these things are still happening. You can just deform them. If you were able to break them easily, that sea would be disrupted, and so we're going to see that that doesn't happen. However, this model has some flaws, because we see that in reality, we would expect the more electrons you have, the better the bonding would be, the stronger the bonding. But we don't see that's the case, because in terms of physical properties, if we look at the D block particularly, we see that we have a trend in each row of the periodic table. As we start in the D block, we have melting points go up and up and up, but then they start going down again as we reach the end of the D block. So starting at scandium, ending at, zinc, we end up having an increase. We start increasing our melting point as we get to iron, chromium in the middle there, and then we start decreasing as we get towards copper and zinc. That is not explained by this model. This model suggests that the more electrons we have, the stronger these properties would be. And we would expect, therefore, that it would be harder to melt a solid with more electrons in it. And so we have to refine this model. And so we don't really necessarily have a sea of electrons. We actually have massive, massive, massive molecular orbitals. And so we've looked at molecular orbitals in terms of simple things, binary, two atoms put together. And we saw that from one atom, if we put 2 atoms together, we get 2 molecular orbitals. But we're going to see that if we put 4 atoms together, then we're going to get 4 molecular orbitals. And those are all going to kind of split in energy as we go through this. So we split, we have a bonding orbital that's lower energy, an anti-bonding orbital that's higher energy. Those can be split further if we have more atoms. And eventually we just keep splitting, and these get so close together in energy that really it's no longer discrete orbitals. We just have millions of splitting. And those get so small, so overlapped, that really we end up with 2 bands. We have filled orbitals and empty orbitals. I mean, it's very, very hard to describe those as discrete orbitals because we have millions of atoms now put together. And I mean millions, I really mean, 10 to the 23rd. Not millions, but quintillions. I don't know the vocabulary to describe bigger numbers, but millions of millions of millions of millions of atoms. And so because all those make a new molecular orbital as you add more and more atoms in, you end up having so many that they just completely overlap. So really, it's very hard to tell an energy difference between any two orbitals because they're so close, because there's so many of them. And so we end up with some that are filled, and those are just a continuous band, and then we have the empty ones as well. And we'll look at this more when we talk about semiconductors later on. So really, this now talks about, this helps us understand why the melting points decrease at the end of the D block. As we start adding more and more atoms and more electrons, the more likely we start filling up these anti-bonding orbitals. Right? We saw that the best situation was if we have, we want everything to be bonding and nothing to be anti-bonding, right? That's going to give us our highest bond order. Highest bond order gives us the strongest bond. And so the best bond order we're going to have is if we have half of our orbitals filled, because half our orbitals will be anti-bonding, half will be bonding. So if we have half of the electrons, and if we're looking at d electrons only, that's 5d, or d5 rather. And so that's right in the middle of the D block. As we start adding more electrons, we're going to start filling these anti-bonding orbitals. And so we see that the bonding becomes weaker as a result. And so we're going to see that the best situation is right in the middle of the D block, not at the ends. And so as a result, we see our strongest intermolecular forces, type ramifications with the middle of the D block rather than the ends, because we have the most filled to empty ratio. All right. So that is how metals look, or alloys. All right, and so if we want to look at ions, so ionic solids, again, are kind of the most likely to be crystalline because of this. They'd like to be alternating positive, negative, positive, negative. We see that the best type of situation here is having completely alternating positive, negative, and so forth. We see here that when we crack these things, when we break them, if you have large crystals of things, they actually shear off each other. They don't just break all just randomly like a piece of paper might. Do I have a nice... I've got an index card. This index card like breaks and you've got these little fuzzy bits everywhere. That doesn't happen with ionic solids. We see that if you break them, they actually shear off each other and you get sheets. You get very distinct lines with each other because they start repelling each other. If you shear them and they don't line up, you end up having them repel each other, and so they flake off. And so you end up with pretty distinct things. One example for this would be mica. Let's take a look at that. That's a mineral. Is this the window? No, I have to make a new one. All right, let me get that going. So if you can see how mica looks, you see all these sheets together. That's what happens when you've got these shearing interactions happening here. So this is a mineral, and you see it's got all these little sheared bits on it. So we have very distinct ionic bonding happening here because these lines of things don't want to interact with each other if they're out of alignment. You want always positive, negative, positive, negative. If you have negatives next to each other, you end up with not very nice sheets. All right, so that's just an example of some of the properties here. Typically speaking, these have extremely high melting points. All ionic substances are solids. because of this very, very favorable way of packing things close together, where we have alternating positives and negatives. That's extremely favorable. And so these are our go-to when we talk about crystalline solids, are ions. And so we see that with ions, when we're talking about how they look in terms of their unit cells, it depends on the size. The size of these things, we always want to minimize negative-negative interactions, minimize positive-positive, and maximize positive-negative in all of these. And so it just depends on the size of our ions. And we're going to see that there's 3 archetypal structures. The cesium chloride is the most primitive, where we have... it's the most basic because cesium ion and chloride ion are roughly the same size. And so we see that that's 2 sets of simple cubic structures with each other. With these, we talk about them as... we can't say simple cubic as simply as positive, negative. We really, when we're looking at unit cells, we're looking at one atom at a time. So if we have positive, negative, positive, negative, positive, negative, positive, whatever, we've got 9 of them there. If we want to look at what the unit cell looks like for one of those, positive, 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 4 negatives in between, maybe a positive in the middle, maybe not, depending on the size. We can have simple cubic, where we've got a positive thing in all 8 corners, maybe a negative thing in the middle, and just kind of offset by that. And then we have negatives all with 8 corners, and those just alternate with each other. They overlap. So the unit structures for the cesium chloride are simple cubic structures. For sodium chloride and zinc blend, which is the zinc sulfide, those are face-centered cubic, and those actually have different numbers of atoms relative to each other, because the zinc and sulfur have different size ratios compared to the sodium and the chloride. And so we see that those... we're going to see that we can generally put various ionic compounds into one of these 3 categories. So cesium chloride is when your atoms are of identical size or very similar. Sodium chloride is when they are the biggest difference. And then the zinc blend, or zinc sulfide, is when they are kind of in between those 2. So we have the smaller cation, bigger anion, but they're not as big of a difference as they are in sodium chloride. And so these all try and pack as close together as possible, again, to maximize favorable interactions and minimize unfavorable ones. All right, any questions so far on these structures? All right, let's talk about molecular ones. So molecular structures are governed by intermolecular forces, whether those are hydrogen bonds, whether those are dispersion forces, whether those are dipole interactions. We're going to see that the properties of these things can change depending on those. We're going to see that benzene and toluene, despite the fact that toluene has more atomic mass or molecular mass because it's got a CH3. These are all carbons at these vertices, and they have hydrogens on the side. Because benzene is completely planar, completely flat, everything is sp2 carbons in there, it can stack together really nicely, and they can maximize their London dispersion forces. And with toluene, you don't have that as nicely. You have to kind of deal with this methyl group there, the CH3 bouncing or bumping into other things. And so we actually see a drop in the melting point because the toluene cannot pack as nicely as benzene can. And then, of course, if we have the hydrogen bonding, that's going to go up a little bit. And so we don't have unit cells when it comes to molecular solids. These are just the molecules themselves and how they interact with each other. So something like sugar would be a molecular solid. You have sugar molecules, sucrose molecules, and those are attracted to other sucrose molecules through intermolecular forces. For sucrose, it's all three: hydrogen bonding, London dispersion, and dipole-dipole interactions. And so those are held together through intermolecular forces. With network solids, these are actually covalently bonded things. We're going to see that this would be something like a diamond or graphite, where we have these things just covalently bonded together, and these networks just go on forever. So a diamond, a 1 carat diamond, has about 10 to the 22 carbon atoms. If it's a perfect diamond, all of those are completely covalently bonded to each other. So 10 to the 22, that's an incredibly high number. And those are just bonded together. As a result, these are pretty strong because they are actually bonded together. They're not going to shear apart. They're not going to have really brittleness to them. They're pretty strong. And they typically have high melting points because they are massive molecular weights. So graphite is one. It's a molecular solid. We have kind of networks of graphite there, and they're connected with dispersion forces between them. So graphite forms these planar sheets together. Graphite therefore conducts electricity. It's pretty interesting because there's delocalized electrons in the benzene. It's pretty cool. So semiconductors, let's talk about them now. These are network solids that behave kind of like molecular solids, where we have them, again, there's so many atoms there, so many atoms in these, that these molecular orbitals keep splitting and splitting and splitting. You end up with filled bonding ones and empty anti-bonding ones. And we have names for these. We have a valence band, which has got all the electrons in it, the bonding electrons. And then we have the conduction band. The conduction band is where electrons can move around. Those are within anti-bonding orbitals. And we're going to see that the difference in energy between all of those bonding orbitals and all of those non-bonding or anti-bonding orbitals is called a band gap. And we're going to see that something that has a band gap of 0 is a conductor. So when those bands overlap together, when there is no band gap, you have conductors. Those are metals. We have no band gap whatsoever. If we take a look at the molecular orbitals for those metals, where was it? Up here, we saw that there's no gap. They are right next to each other. They move freely between them. But if you have a band gap, you have an energy difference between those. And if your energy difference gets too big, say above 3.5 electron volts or so, you become an insulator. So we're going to see that semiconductors have band gaps that are in between 0 and about 3.5 electron volts. And an electron volt is roughly 300 kilojoules per mole or so, just so you can have a frame of reference. So it's a pretty big gap there. So a single electron volt is about 100 kilojoules per mole. The about 3.5 electron volts that makes something an insulator, that's about 300 kilojoules per mole. So with these are typically made with semi-metals because they're neither conducting nor insulating. They're in between. We're going to see that we can mess with the properties of these by adding an extra stuff. So we're going to see that these ones have gaps in their bands. Again, we're looking between about 0 and 3.5, and so somewhere around there. And again, of electron volts, which goes between about apparently 7 to 300 kilojoules per mole. That's the energy difference between those two sets of molecular orbitals. And so we're going to see that these these things tend to have 4 valence electrons. That's kind of the magic number for semiconductors, though we see that sometimes we put things with 3 and 5 together to get an average of 4. So gallium arsenide is a common semiconductor material. And we're going to see that that band gap is very useful for us because that's going to have a restriction on when things can flow. Conductors, there's no barrier to energy, so they can just completely flow at any time. With insulators, they don't flow. Electrons don't flow. But with semiconductors, they flow at a certain time. And that's when we can get great properties. That's why they're so useful for us. All of our computer chips are semiconductors because we want them to do certain things when we reach certain voltages. And so it's a very useful thing. And we can mess with these by adding in different atoms. We can mess with these bands. So let's say we have pure silicon. Silicon has 4 valence electrons, and so it's called undoped. We don't have extra atoms in there. It's all silicon, and it's got a very specific band gap. Silicon has an average of, or it's got all 4 valence electrons, right? And so we have half of them in the valence band, half of them, and none of them in the conduction band. If we add in something that has more than 4 valence electrons, like phosphorus or arsenic, we're going to start adding in more electrons to our molecular orbitals. The more electrons that we put in, we start filling up the conduction band. And so these are called negative type semiconductors, N-type semiconductors. And so those have extra electrons. And those are going to help increase our conductivity. In fact, even just tiny amounts of phosphorus added to silicon increases your conductivity by millions. Millions. So when you're looking at computer chips, these impurities are very, very important. And so we see that in order for computer chips, manufacturers like to have silicon that is 99.9999999% pure. Incredibly pure, because these band gaps are so specific. They want their exact band gap, so they want the purest possible silicon. If you have impure silicon, or germanium or gallium, whatever you're using, then your band gap can vary. And so you can't get consistency. And so that's the point here. However, it's if you want something to conduct, you can do this by doping it specifically with phosphorus or arsenic atoms, giving you negative silicon, a negative semiconductor. Or you can put positive things like aluminum, like gallium in there. Those have 3 valence electrons, so you're going to lower your overall valence, giving you a positive type semiconductor, a p-type semiconductor. And you can put p-types and n-types together, and those will conduct between each other. And so you get, again, very specific band gaps for whatever your purpose is. As long as you know your band gap, you can control stuff really well. And so these are very useful materials for us. All right, so cool stuff there. Any questions so far? Looks like we are going to get through all of it today, so that's good. All right, let's look at polymers. So polymers are long chains, networks of repeating units. So these are plastics, right? So these are our plastic bags. This Sharpie that I randomly have here is made of polypropylene. That's a 3-carbon unit that's being repeated over and over again. Polyethylene, which would be this structure shown here, is just single carbon chains bonded together. Those are ethylene molecules that bond together, forming a long chain called polyethylene. Polyethylene is plastic bags Let's see. Yeah, I've got some polyethylene here, perhaps. Maybe. This may be polyethylene, I don't actually know. But polyethylene, it's a plastic. All of our plastics are polymers. Whatever those happen to be. Polyethylene is your plastic bags, and milk cartons, milk jugs, that sort of thing. Polypropylene, your pens, that sort of plastic. You have things like polyethylene tetrathalate, which would be something like this water bottle. Polycarbonate, which are Nalgene bottles. Polyesters, which are you can make into clothing. All these sorts of things are polymers. In fact, why am I doing this? I have examples on the next slide. Polyvinyl chloride, PVC, very important for plumbing. Polystyrene is styrofoam. What else do we have here? Nylon is another one. Polyurethane is foams. So these are all very useful things. However, of course, these are plastics. They're very hard to break down, as we know. And so these sorts of polymers, their hallmark thing is that they're made of repeating units of the same carbon-based substance over and over and over again. And so we might describe these as having that unit and having n of those linked together. And we can make these in a couple ways. We can have them added together, called addition polymers, where we just add these things together. We're going to break pi bonds and make sigma bonds within them, and we end up with long chains. Or we can make condensation polymers, which we actually lose something as we put them together. And so this is stuff that's covered in organic chemistry, of course, but you'll make byproducts by getting rid of some amount of atoms. And you're not necessarily breaking pi bonds and making sigma bonds. You're making sigma bonds and breaking sigma bonds with condensation ones. And so you're just joining them together. And these are all often either alternating things, or you can have the same thing with multiple functionality on different sides. Like amino acids, when they come together like this, they're condensation polymers. And those, when they come together, they also produce water as a byproduct. So if we take a look at nylon, you have the amine side of nylon and the carboxylic acid. These are things we'll learn in OChem. Put those together, you get an amide bond, like a peptide. That's the bond in between them, and you're going to make some water at the end there. And so you end up just putting these things together. So you have the diamine, you have the adipic acid, diamine, adipic acid, diamine, adipic acid, and these just grow in steps over and over again. You can also cross-link them. And interesting polymers, you can have crystalline polymers, you can have amorphous polymers, and they can have different regions that give them different properties. So we're going to see that those will vary here. And so interestingly, polyethylene, just CH2, 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 CH2 forever, depending on how crystalline it is,